Grounding a 15 kilovolt bus through a wound-type current transformer and safely working on it is not acceptable. This is due to several reasons. Firstly, primary energization. If a current flows in the secondary of the current transformer, the primary side can become energized to an extremely high voltage. This happens because the current transformer acts as a step-up transformer, with the secondary current inducing a proportional voltage in the primary winding, ideally infinite if the primary were perfectly grounded. Secondly, safety concerns. The high voltage on the primary of the current transformer poses a significant safety hazard. Contact with the energized current transformer could result in severe electrical shock or death. Thirdly, equipment damage. The high voltage on the primary can damage the current transformer itself and other equipment connected to the bus. The correct grounding procedure is to properly ground a 15 kilovolt bus with an appropriate grounding device such as a grounding stick or grounding mat. The grounding device should be rated for the voltage of the bus and applied in a way that ensures a good electrical connection. If direct grounding is impossible, alternative methods can isolate the bus for safe work. These methods include 1. Using a high voltage circuit breaker to disconnect the bus from the power source, 2. Applying phase-to-phase insulation to the bus to prevent current flow, and 3. Using a portable grounding device, like a portable grounding stick, to isolate the bus from surrounding equipment. When dealing with high voltage systems, safety is paramount. Never compromise on proper grounding procedures and always use appropriate equipment. Ensure all grounding devices are correctly rated for the system voltage and are properly installed. Double-check all connections before commencing work. High voltage electricity poses serious risks, and shortcuts can have fatal consequences. Always adhere to established safety protocols and seek guidance from experienced professionals when necessary. It is critical to understand the function and hazards associated with current transformers, especially in high-voltage applications. These devices are designed to measure current, but their operation can create dangerous voltage conditions if not properly handled. The principle of operation of a current transformer involves a primary winding carrying the current to be measured and the secondary winding connected to a measuring instrument. The current in the secondary winding is proportional to the current in the primary winding, with the ratio determined by the number of turns in each winding. Under normal operating conditions, the secondary winding must always be connected to a burden, which is a low impedance measuring instrument or a short circuit. If the secondary winding is open-circuited while current is flowing in the primary winding, a high voltage can develop across the secondary terminals. This is because the current transformer attempts to maintain the ampere-turns balance between the primary and secondary windings. With no current flowing in the secondary winding, the voltage rises to a level sufficient to magnetize the core and satisfy the ampere-turns balance. The voltage can reach several kilovolts, posing a significant shock hazard. In the scenario of grounding a 15 kilovolt bus through a current transformer, the primary winding of the current transformer is effectively connected to the high voltage bus. If the secondary winding is open-circuited or has a high impedance, the primary winding can become energized to a dangerously high voltage. This is because the current transformer will attempt to maintain the ampere-turns balance, resulting in a high voltage on the primary side. This situation is particularly hazardous because it can create a false sense of security. Workers may assume that the bus is grounded and safe to work on, when in reality, it is energized to a lethal voltage. It is essential to use proper grounding techniques and equipment when working on high-voltage systems. Grounding sticks and grounding mats are designed to provide a low-impedance path to ground, ensuring that the bus is de-energized and safe to work on. These devices must be properly rated for the voltage and current levels of the system. Before commencing any work on a high-voltage bus, it is crucial to verify that the bus is properly grounded and energized. This can be done using a voltage detector or other appropriate testing equipment. Never rely solely on visual inspection or assumptions. Always confirm the absence of voltage before touching any part of the system. In addition to proper grounding techniques, it is also important to use appropriate personal protective equipment such as insulating gloves and sleeves. These items can provide protection against accidental contact with energized parts. Always follow established safety procedures and guidelines when working on high-voltage systems. These procedures are designed to minimize the risk of electrical shock and other hazards. If you are unsure about any aspect of the work, seek guidance from experienced professionals. Remember, safety is always the top priority. Never take shortcuts or compromise on safety procedures. High-voltage electricity is unforgiving, and mistakes can be fatal. Current transformers are not designed for grounding purposes. They are designed to measure current, not to provide a path to ground. Using a current transformer for grounding can create a dangerous situation, as described above. Always use proper grounding equipment and techniques when working on high-voltage systems. The selection of appropriate grounding equipment depends on the voltage and current levels of the system. Grounding sticks and grounding mats are available in various sizes and ratings. Choose equipment that is specifically designed for the application. The application of grounding equipment must be done correctly to ensure a reliable connection to ground. Grounding sticks should be securely clamped to the bus and connected to a verified ground point. Grounding mats should be placed on the ground and connected to a verified ground point. The ground point must be a low impedance path to earth. A ground grid or a driven ground rod can be used as a ground point. The resistance of the ground path should be as low as possible, ideally less than 1 ohm. Regular inspection and maintenance of grounding equipment is essential to ensure its proper functioning. Grounding sticks and grounding mats should be inspected for damage and wear. Ground connections should be checked for tightness and corrosion. Any damaged or worn equipment should be replaced immediately. Training is essential for workers who work on high-voltage systems. Workers should be trained in the proper grounding techniques, the use of grounding equipment, and the hazards associated with high-voltage electricity. Training should be conducted by qualified instructors and should include both classroom instruction and hands-on practice. Regular refresher training is also important to keep workers up to date on the latest safety procedures and equipment. In addition to the above, it is important to have a written safety plan in place for all work on high-voltage systems. The safety plan should outline the procedures to be followed, the equipment to be used, and the responsibilities of each worker. The safety plan should be reviewed and updated regularly. A job hazard analysis should be performed before commencing any work on a high-voltage system. The job hazard analysis should identify the potential hazards associated with the work and the steps that will be taken to mitigate those hazards. The job hazard analysis should be documented and reviewed by all workers involved in the work. Communication is essential when working on high-voltage systems. Workers should communicate with each other to ensure that everyone is aware of the potential hazards and the steps that are being taken to mitigate those hazards. A clear and concise communication protocol should be established and followed. Coordination is also essential when working on high-voltage systems. Work should be coordinated between all parties involved, including the utility company, the contractor, and the workers. A coordination meeting should be held before commencing any work to discuss the scope of the work, the schedule, and the safety procedures. Supervision is essential when working on high-voltage systems. Work should be supervised by a qualified supervisor who is experienced in high-voltage work. The supervisor should be responsible for ensuring that the work is performed safely and in accordance with the established procedures. Documentation is essential when working on high-voltage systems. All work should be documented, including the date, time, location, and description of the work, the equipment used, and the safety procedures followed. Documentation should be maintained in a secure location and should be available for review. Audits are essential to ensure that high-voltage safety programs are effective. Audits should be conducted regularly by qualified auditors who are independent of the work being audited. The audit findings should be documented and used to improve the safety program. Continuous improvement is essential for high-voltage safety programs. Safety programs should be continuously reviewed and improved based on the results of audits, incident investigations, and feedback from workers. The goal of continuous improvement is to create a safer and more efficient work environment. In conclusion, grounding a 15 kilovolt bus through a current transformer is not acceptable and poses significant safety risks. Proper grounding procedures, equipment, training, and safety plans are essential to ensure the safety of workers and the integrity of equipment. Always prioritize safety and seek guidance from experienced professionals when working on high-voltage systems. The principles discussed here apply generally to high-voltage systems, although specific voltage levels and equipment types may vary. Always consult with qualified engineers and adhere to applicable codes and standards for the specific installation.